guys, William Talbot here for CSE 545, and we're going to be covering the vertex cover problem today. So a little bit of an agenda for the presentation. I'm going to go over an intro, explaining the vertex cover problem, my algorithm approach, my code, the results overview from all the tests that I ran, and then a conclusion. So what is the vertex cover problem? It's a classic optimization challenge in graph theory. So imagine you have an undirected graph, a network of vertices connected by edges, and the goal is to find the smallest possible subset of these vertices that covers all the edges. So in other words, every edge in the graph should be connected to at least one of the vertices in our subset. So this means identifying which vertices are essential to touch all edges with the fewest selections possible. So for example, if a vertex connects to multiple others, it can be a strategic choice as it covers multiple edges in one go. So solving this problem helps in optimizing resources across networks, and it definitely has its applications in fields like logistics, network security, and resource management. So a little bit of an in-depth explanation. Let's dive into what the vertex cover problem is all about. So imagine you have a network like a web of cities connected by roads. In graph terms, these cities are called vertices, and the roads between them are edges. So the goal in the vertex cover problem is to pick the smallest number of cities or vertices so that every road in the network is connected to at least one of our chosen cities. So why is this important? Well, in computer science, this is known as a classic optimization problem because it's about minimizing resources, but it's also a tough one, so that's why we call it an NP hard, meaning that there's no quick solution to find the smallest vertex cover in every case. So to make it simpler, we often look for an approximate answer instead of the exact smallest cover. And this problem is central to many fields, from logistics to network security, as it helps us understand efficiently manage resources within networks. So my approach to the algorithm, to take on this problem, I developed a hybrid algorithm that combines a genetic algorithm with the wisdom of crowds approach. And my main aim was to see if incorporating collective intelligence into the evolutionary algorithm could help improve heuristic solutions for this complex problem. So let's start with the genetic algorithm. I tailored it specifically for the vertex cover problem, using a mix of genetic operators for recombination, like one point and uniform crossover. For mutation, I use swap and inversion to keep genetic diversity high. Elitism helped carry forward top-performing solutions across generations, while tournament selection maintained a balance between exploring new options and refining existing ones. So to test the algorithm, I created a set of predefined tree graphs with nodes ranging from 10 to 35, providing a pretty complex range. So each graph had randomly generated edges and node coordinates to simulate realistic scenarios, testing the algorithm's scalability. So wisdom of crowds was integrated by collecting the best solutions from previous generations into what I called a wisdom pool, and this pool helped guide the genetic algorithm towards better solution by using patterns from successful past runs. By leveraging these patterns, the genetic algorithm could, in theory, reach more optimal areas in the solution space more efficiently. I also experimented with using a greedy algorithm to initialize part of the population, giving the genetic algorithm a strong starting point that could potentially speed up convergence to higher quality solutions. So for my experiments, I tested the genetic algorithm with the wisdom of crowds hybrid using various parameter combinations, and this included trying different crossover and mutation methods, adjusting mutation rates, changing population size, and using both the greedy initialization and the wisdom of crowd approach. Automated these combinations and ran them in parallel, which made the testing process much more manageable. Visualizations were crucial in understanding the results. I tracked fitness across generations and displayed the vertex covers directly on graphs. Um, these visuals help me compare different configurations and observe how the algorithm evolved over time. And ultimately, my goal was to see if adding the wisdom of crowds to a genetic algorithm could genuinely improve the solution quality for the vertex cover problem over a standard genetic algorithms. So through systematic testing and analysis, I aim to explore whether collective intelligence could effectively combine with evolutionary algorithms to tackle the NP-complete problem. So for my code, I structured each solution as a chromosome using a binary vector to represent which vertices are part of the cover. In this vector, each position corresponds to a vertex, with 1 indicating inclusion in the cover and 0 indicating exclusion. And this binary representation allows us to easily evaluate the fitness of each chromosome based on its edge coverage. Essentially, solutions that cover all edges with fewer vertices score higher, while those leaving edges uncovered are penalized. And I achieved this evaluation with the calculate fitness function, ensuring that complete coverage was prioritized. The initial population is crucial in any genetic algorithm, and for this I generated solutions using both random assignments and a greedy algorithm. The greedy approach prioritizes vertices with higher connectivity, which provides a smart starting point by covering edges more efficiently, and by combining these diverse solutions, I aim to give the genetic algorithm a broad range to explore right from the beginning. To further enhance exploration, I integrated 2 crossover methods. The first one, the one-point crossover, it splits chromosomes at a random point, inheriting segments from each parent. And the second, uniform crossover, which mixes genes from each parent with equal probability, promoting diversity by blending characteristics across chromosomes. For mutation, I implemented both swap mutation and inversion mutation. Swap mutation swaps the states of 2 randomly chosen vertices, allowing for small tweaks that help fine-tune solutions. And on the other hand, inversion mutation reverses a random subsequence of vertices, introducing larger changes to help the genetic algorithm escape local optima. Parent selection was managed by the tournament selection function, where subsets of the population compete and the fittest are chosen as parents. And this approach strikes a balance between maintaining diversity and preserving high-quality solutions, which helps prevent premature convergence. So, consistent with the various TSP problems we've done this semester, incorporating the wisdom of crowds approach, I maintain a wisdom pool, a collection of the best solutions from previous generation, and this collective intelligence was leveraged by guiding new generations towards successful patterns from the past. So in practice, the wisdom of crowds algorithm function integrates the wisdom pool to influence new chromosome creation, combining the strengths of the best solution. The entire genetic algorithm process um, is managed by the run GA function. It initializes the population and then applies selection, crossover, mutation, and fitness evaluation iteratively across generations. And I designed this as a modular system with function pointers, allowing easy switching between operators and providing flexibility for experimentation with different parameters. So to make the program interactive, I included prompts for selecting parameters like crossover and mutation methods, population size, and number of generation. Once the execution finished, the program outputs the best solution, showing its progression and fitness and visualizing the vertex cover on the graph itself. I also developed a fitness graph visualization with the generate fitness graph function, which tracks how fitness improves over generation. And this helps analyze convergence patterns and assess how different configurations impact the solution quality. In terms of data, I used tree graphs with varying node counts, 10 to 35, as a test bed for the genetic algorithm. Tree graphs provide minimal connectivity and a predictable structure, which is ideal for testing vertex cover algorithms. So and by systematically generating these graphs, I created a standardized data set that supported consistent testing across various configurations. Each configuration results included fitness scores, average vertex counts, runtime efficiency, and observations from visualizations of the vertex cover. So, for example, in smaller graphs, optimal configuration scored higher with fewer vertices and shorter runtimes, while in larger graphs I observed similar patterns but with more pronounced differences in the fitness stability between optimal and non-optimal configurations. So overall, This structured and modular approach allowed me to test and compare different configurations and allow me to gain insights into how collective intelligence and genetic algorithms can effectively tackle the vertex cover problem. So a quick overview of the results. So to ensure reliable testing for the genetic algorithm, I utilize a systematic approach to create undirected graphs ranging from 10 to 35. Each graph allowed me to test different genetic algorithm configurations under control conditions, which made it possible to draw meaningful comparisons about each configuration's efficiency and effectiveness in solving the vertex cover problem. So for each graph size, I experimented with multiple configurations. I varied crossover methods using both uniform and one-point mutation rates from 0.05 to 0.75 and mutation strategies like swap mutation. I also tested with and without heuristic approaches such as the greedy algorithm and the Losing crowds technique, and collected data on fitness score, vertex counts, run times, and insights from visualizing the vertex covers and fitness progression. So across all graph sizes, the optimal configurations consistently outperform the least optimal ones. For example, in the 10-node graph, the best setup achieved a fitness score of 0.6 with an average vertex count of 4 and a runtime of just 0.009 seconds. And in contrast, the least effective setup had a much lower fitness score, slightly more nodes in the cover, and took longer to run. In the largest 35-node graph, the optimal configuration reached a best fitness score of 0.67647 with an average vertex count of about 19.6 nodes and a runtime of 0.011 seconds. So fitness graphs confirm this, showing that the optimal configurations displayed smooth, steady trends indicating consistent convergence. On the other hand, least effective setups had erratic fitness patterns. So altogether, these results highlight that certain configurations can significantly enhance the performance and efficiently solving the vertex cover problem. So focusing on graph node 20, starting with the least optimal configuration on the far left, you can see in the vertex cover visualization that there are more green nodes than necessary, and these extra nodes indicate inefficient coverage. In other words, the algorithm included more vertices in the cover than needed to cover all edges. And this is a clear sign of instability in the solution. And if we look at the corresponding fitness graph next to it, we can observe highly erratic fluctuations, and this jagged pattern indicates that the algorithm struggled to converge with fitness values jumping up and down due to the high mutation rate. And this instability also affected runtime, leading to slightly longer processing times as the algorithm repeatedly veered away from optimal solutions. But in contrast, on the right, we see the most optimal configuration. The vertex cover visualization here is more streamlined with fewer green nodes, indicating a minimal and efficient cover that achieves full edge coverage. And this efficient selection of vertices where it reflects a well-optimized solution. In the corresponding fitness graph, notice how line is much smoother and steadier. And this indicates consistent convergence with the algorithm, steadily improving and refining solutions over generations than just erratically jumping around. So the use of the greedy algorithm and wisdom of crowds here contribute to the steady progress by guiding the genetic algorithm towards promising solutions and balancing exploration and exploitation. So in summary, these visuals, they underscore the performance differences. The least optimal configuration displayed scattered and vertex coverage and unstable fitness progression, while the most optimal setup achieved efficient coverage with a stable, smooth convergence path. And this comparison highlights how specific configurations like adding collective intelligence and adjusting mutation rates can significantly impact the genetic algorithm's ability to solve the vertex cover problem efficiently and accurately. So for the 20-node graph, I analyzed both the least optimal and most optimal configurations to understand the genetic algorithm's effectiveness. So starting with the least optimal configuration, which used uniform crossover and a higher mutation rate of 0.75 without applying the greedy algorithm or Wilson and Krauss technique, and the results were subpar. This configuration led to a worse fitness score of negative 0.73684 with a large variation between best and worst scores, indicating instability. The fitness graphs show erratic fluctuations reflecting difficulties in maintaining consistent progress, and In the Vertex cover visualization, more nodes were selected than necessary, highlighting inefficient coverage and unreliable convergence. And the runtime was also slightly longer at around 0.0105 8 seconds due to excessive mutation affecting stability. So in contrast, the optimal configuration using uniform crossover, swap mutation, and incorporating both the greedy algorithm and wisdom of crowds technique, it performed slightly better. It achieved a best fitness score of zero point 0.6 with stable average and worse scores, indicating consistent convergence. The fitness graph for this configuration showed a smooth, steady trend, illustrating a balanced exploration and exploitation. So in the vertex cover visualization, we'll see a well-connected minimal cover with an average vertex of 8 nodes, effectively approaching the minimum coverage needed. So this setup ran efficiently with a runtime of approximately 0.0095 seconds. So overall, the optimal configuration provided a stable, efficient solution, while the least optimal setup struggled with consistently, leading to node selections and less effective coverage. So kind of final takeaways. In conclusion, the consistent success of optimal configurations reveals more than just parameter tuning. It highlights the underlying dynamics of genetic algorithms when applied to complex optimization problems like the vertex cover. Optimal setups incorporating structured crossover, controlled mutation rates, and heuristic methods such as greedy algorithms and wisdom of crowds provided a balanced approach to exploration and exploitation, and this balance allowed the algorithm to effectively the solution space, reducing randomness and ensuring that it built on successful solutions rather than drifting aimlessly. So the advantage in these configurations lies in their ability to maintain genetic diversity without sacrificing convergence. For instance, swap mutation introduced subtle variations that help refine solutions, while techniques like wisdom of crowds aggregated successful patterns, guiding the algorithm towards promising areas of the solution space. And this collective intelligence, coupled with controlled exploration, prevented the genetic algorithm from getting stuck in suboptimal regions or being overwhelmed by randomness. On the other hand, the least optimal configurations with high mutation rates and no heuristic guidance introduced excessive variability, and this randomness led to erratic fitness patterns and inefficiencies as the genetic algorithm struggled to build coherence across generations. So the high mutation rate acted almost like a reset button, disrupting promising solutions rather than enhancing them. So ultimately, these findings emphasize that in genetic algorithms, especially for NP-hard problems like the vertex cover problem, success hinges not just on the parameters chosen, but on how well those parameters facilitate a structured, adaptive search process. So integrating domain-specific heuristics and managing mutation levels thoughtfully allows the genetic algorithm to evolve in a way that's both robust and efficient. So future work could explore adaptive mutation strategies that dynamically adjust based on convergence progress, potentially unlocking even greater efficiency and stability for similar complex optimization tasks.